在里面讲，他前面会讲，只要当年作为实验，你早就多了。是一个 term 谁看？你要这两个就是一个 term。错了。看一下他的 abstract。没有办法。哦，这边有几个。找工作。那是他。对呀。
But he didn't say he wasn't going to come, so he won't be there.
I didn't see him this morning.
He's not well, so I guess he looked here just in time.
Something incredibly minor, I forgot what it was.
Hi. Francisco says it's live, so I guess it is working.
There's like a minute delay.
It's a very long delay. Yeah, my external committee member is not online. And my advisor is not online. I tested this last night with Romy. She was at home. It's great.
Yeah, this thing works great.
Yeah. Rich, I got some Indian stuff from the place we went to. So
Oh,
try
okay.
it.
Hi, yeah, I think we met Rich. Dan.
Okay. Yeah, I'm also the president of EC20, and we collaborated.
You do computer vision. And computer science.
Okay, which
I'm done for a while.
often is, often
There's a bunch of,
science,
yeah.
of course.
Yeah, in the-
You're here.
Oh, yeah. Oh, okay.
Hello, everybody.
I'm with networking.
So I don't see Victor on Skype. And I texted him. He hasn't replied yet.
I'll give him a few minutes.
I'm sorry to hear that.
Yeah, it's a bit work-free, but actually much better today. Finally, almost away.
Days you're not allowed to be sick on the day you're skipping events.
Yeah, no, we went to Women's just last week and it's a nasty viral infection here.
I read something about a bacteria in Lake Erie.
Bacteria in the lake area.
Well, that's where the Niagara River starts.
I
So.
suspect the 6-hour delay at the airport somewhere. So many
6
people
hours?
was waiting 6 hours at Newark to get a flight.
That's what's right. I've driven to Buffalo in 6 hours.
Yeah,
Yeah. What? Get there in 6 hours. So it was longer to fly than drive.
Yeah. What's the thunderstorm front from Canada down past BC? There's no route available. No way to get through.
Anywhere. Hi, Ray, how are you?
No, he insisted on scanning and signing it. All the graduate school said no, but I'll just do what he said.
Okay. That's how I'm still not perfectly well. It doesn't feel like a flower. That's good. It's more life actually. That ground stories that you were asking for them.
Oh, yes, yes, you know what, it's a little bit late though, because we had the, prepared but I'm gonna say that we'll go back to the Senate meeting where we'll also raise all of these points again. It's a 12-hour flight, I'm hoping there are no delays. I don't want a 6-hour delay and then a 12-hour flight.
He replied, he said he was trying to call the meeting link, so now it will come on Skype. The calendar.
Just dial them on the regular phone.
Let me see. Hi, Victor.
Hey, Victor.
I finally got you.
Yes.
All right, we have everybody here. The other committee members, Kristen, Dana, and Rich Martin are here. We also have a pretty large audience, and Ray is also here. I think, Victor, you know each other.
Hi, Victor.
Hey guys, how are you? Hi. Excited about Shubham's defense. Let's do this.
Yes, let's go right ahead.
Thanks, Marco, and thanks everyone for being here today. I'll be honest, I never thought this day would come, so I'll just go ahead and start. I'm going to talk about my experiences designing inertial and camera support systems for supporting smart intersection applications. Every day we witness people walking in the streets, talking, texting, listening to music, barely paying attention to their surroundings. Clearly, technology distractions are having a negative impact on pedestrian safety. In fact, SMOMBY, a combination of smartphone and zombie, was Youth Word of the Year in 2015, and it alludes to a distracted driver. To tackle the rise of SMOMBYs, New York City started painting look signs at crosswalks to alert in an attempt to alert pedestrians who text when crossing the street. A city in Germany installed flashing traffic lights on the sidewalks to alert pedestrians when they enter the street, and some city in China decided to just make a separate lane for distracted walkers. Pedestrians account for 15% of all traffic fatalities. In the last decade, more than 47,000 people died while walking on the streets. And distracted pedestrians are just one of the many problems in our urban cities, among others such as recurring and non-recurring traffic congestions, longer than average wait times, and parking limitations. Let's look at some of the current urban traffic management schemes. The first here are in-road detectors. They are tiny loop inductors usually dug up into the street, and they detect vehicles as they pass over them, keep account, control traffic lights. Then we also see a lot of RFID and radar systems which can track a vehicle's speed and somehow also keep track of where vehicles are going and where there's more traffic. But these techniques require added hardware. They're not easily scalable because somebody has to go out and install all of these devices, and they're not cost effective. Over the last few years, we've seen a steep rise in the number of surveillance cameras surrounding us, which also involves a traffic operator sitting in a remote room staring at a wall full of displays, estimating and predicting traffic congestion, detecting unusual events. Recently, we've also seen a rise in the number of smartphone applications that allow us to report traffic congestion, maintenance sites, potholes, bumps, or even when cop cars are on the side of the street. But these approaches are not fully automated, they're obtrusive, they require direct human intervention. We're looking for a large-scale, low-cost solution for urban cities that understands our environment, that knows how we move through the urban landscape, and do all of this unobtrusively. 50% of the world's population lives in cities, and these cities are already equipped with technologies that could transform our infrastructure. Our cars, our smartphones, our cameras, traffic lights, they all have sensors and mini computers in them that can do powerful things. And now more than ever, we're connected to remote servers that can process this stream of information coming in from all the sensors and support novel beneficial applications, such as pedestrian safety, traffic volume monitoring, road conditioning monitoring. So my dissertation in the last few years, I've worked on enabling sensing techniques on these existing devices to support smart services. Certainly, we can deploy more sensors in our cars, in our traffic lights, by the side of the road, but before that, I want to pause and ask, are we using existing sensors efficiently? Are we using them to their full capacity? So some of the questions that I'm trying to answer is, what are we doing? We're taking a step towards smart cities, one intersection at a time. Because technology has influenced every aspect of our life, but our traffic infrastructure is still pretty dated. And we're targeting dense urban environments, which is seeing a rise in traffic fatalities, congestion, and other traffic-related problems. We want to do this by showing that even when precise positioning does not work in urban environments, relative positioning and motion patterns are contexts that can be used for supporting applications pertaining to safety and analytics. So we primarily worked with three sensing modalities. The first was sensors on the smartphones, which includes GPS, inertial sensors, and also the smartphone camera. The second is the class of wearable sensors, where I focused a lot on shoe-mounted inertial sensor units. And the last is infrastructure camera. And we picked surveillance cameras because they're everywhere, and most cities are trying to add more and more surveillance cameras to their network. We use the first two sensors to demonstrate how we can support pedestrian safety applications, and we use surveillance camera to build a platform that can support video analytics services. But reusing sensors is harder than deploying sensors for primarily a specific purpose. The first challenge is that we have to preserve the original functionality of the sensor. So if a camera was installed for a specific purpose, say to look for cars that turn on red, it has to be able to do that, and we want to support more services on top of that. Second, these sensors are not optimally placed or positioned for what we want to do. For example, if you're driving and we want to use your phone to do some context sensing, we have to take into account that your phone could be mounted on the windshield, it could be loosely placed in the cup holder, or it could also be in your pocket. Then, because we're concerned about traffic participants, precise outdoor localization is very important, which means that we need GPS and other added functionalities that we can to support this precise localization. And outdoor environments are very noisy. There's a lot of things, we're walking around, we're driving around, we get off the car, and our context changes very rapidly. So this is how my talk is structured. I'll start by talking about GPS-based pedestrian risk detection, then move on to how we use shoe-mounted sensors to profile the ground that a person is walking on. I'll discuss crossing detection algorithms that we built on smartphone cameras, and the last topic will be a scheduling algorithm that we built for infrastructure cameras. Our pedestrian safety work is based on the premise that most pedestrian fatalities are inherently preventable, and most of them also occur when a pedestrian is entering the street. So we focus on detecting when somebody is entering the street. If you remember the look signs painted, they're also painted at the entrance to a street. The flashing lights in Germany, also at the entrance of a street. So we're trying to do a digital version of that. Can we bring that warning to the pedestrian's phone, because the pedestrian is usually texting when entering the street. Our strawman approach uses GPS sensor on the smartphone. Using the GPS, we know what are the streets around you, what your position is, and your heading is, and we want to combine this information to predict where you're going. If I know where you're going, then we can also predict if you're about to enter a street. So we extrapolate the heading by a distance d and continuously monitor this predicted path. When the predicted path intersects with a street, we know that the person can be warned to look up from his phone and be aware of his surroundings. While this approach works well in suburban and rural environments, GPS limitations are well known in urban cities. We also tried it out in New York City. The blue and the green are traces that we collected using a smartphone, and the red line shows the path that we walked. And we can see that in such urban canyons, modern phone GPS receivers frequently reach errors of up to 30 to 40 meters. And since sidewalks are only a few meters wide, clearly GPS accuracy is not enough for street-sidewalk distinction. So what are the challenges? It turns out that detecting exactly when a pedestrian transitions from a sidewalk to street is indeed challenging. First of all, we need precise sub-meter localization in urban canyons. Second, let's say even if we had the exact position, if we knew exactly where a pedestrian was, we would still need to know if that position was on a sidewalk or a street, because sidewalks are safe walking locations, whereas streets are not. Then the urban environments are noisy. Pedestrians are constantly walking around trash cans and poles and carts and running across the street. And individual walking styles vary a lot. People have different gaits, they have different walking styles and different attitudes towards crossing streets. So we want to tackle all of these challenges, but let's look at some of the existing solutions first. The first here is WalkSafe, which uses a pedestrian's smartphone's rear camera to detect oncoming vehicles. And this is targeted for when a pedestrian is talking on the phone and crossing the street. The drawback of this approach is that the car needs to be in direct line of sight of the camera, and if a car approaches from the other side, the system cannot detect or warn the pedestrian. The second is the one that most car manufacturers seem to be going this way, which is installing a camera inside the car. So this stereo camera looks for pedestrians in the camera's field of view and tries to warn the car if there's a pedestrian in its path. But this again needs the pedestrian to be in direct line of sight and does not work well if it's too dark or if the pedestrian is blended with the surroundings. The last approach is Wi-Fi based beacon stuffing. It's called Wi-Fi honk, which enables exchanging messages between cars and pedestrians. But this approach relies heavily on GPS. So all the drawbacks of GPS apply directly to this system. Which brings me to our approach of using shoe-mounted sensors for ground profiling. To make street-sidewalk distinction, we decided to detect features that actually separate them. If we can detect the features that separate streets and sidewalks, then we can detect the transitions. And we realized that ramps and curbs primarily separate streets and sidewalks in urban areas. When somebody walks on a sidewalk, the ground is pretty flat, and the slope of the ground doesn't change much. But when they walk down the sidewalk ramp, there's a sharp decline in the slope. And what I'm trying to answer is, can we use sensors to detect the subtle slope incline and identify when somebody is about to enter the street? To detect ground features, sensors are best placed on the shoes. And shoe-mounted sensors have been proliferating in the fitness tracking world. They have been used a lot for indoor localization, step counting, and debt reckoning. So we decided to use these sensors, but not for tracking a pedestrian's motion, but to sense the environment, to sense the ground that he's walking on, and more precisely the slope of the ground, and create a profile. Our prototype here includes an accelerometer, a gyroscope, a magnetometer, and Bluetooth to communicate readings to the smartphone. So I'll give you an overview of crossing detection and then go over in some details. We take the shoe sensors and extract pitch, yaw, and magnitude, of which pitch and yaw are tilt angles. Then we use these readings to profile every step. For every step, we extract these three features, which is slope, force, and yaw, and use that to detect ramps and curves. And I'll discuss in details how we do that. We also apply some guard zone filtering method to actually get rid of false positives that are generated during walking in the outdoor environment. So to measure the slope of the ground, it's important to first measure the inclination of the foot. And the most straightforward way of doing that is through an accelerometer. An accelerometer can measure the force of gravity. So it can be used to measure the tilt by looking at relative changes in this force that's acting on the shoe. For example, the first figure here, the foot is flat on the ground, and we can see that all the gravity is acting along the z-axis while none of it is on the x-axis. When the foot tilts a little, say by some angle x, then now we see some distribution of gravity on the x-axis. And this ratio of the gravity distribution gives us the new angle, which is x in this case. The foot tilts further and we can get the new angle that the foot tilts. But accelerometer readings suffer from vibration errors. An alternative way of getting this tilt is by using a gyroscope. A gyroscope continuously measures angular velocity along all its axes. So if we integrate the gyroscope readings along the y-axis, it gives us the forward tilt or the pitch of the shoe. If we integrate all the gyroscope readings along the z-axis, it gives us the horizontal rotation of the foot. But gyroscope, although it allows us to track precisely small movements, it suffers from integration errors that accumulate over time. To overcome the drawback of individual sensors, we combine both these sensors by using a complementary filter. A complementary filter is a combination of a high-pass filter and a low-pass filter, and it gives us more accurate measurements for the pitch or the forward inclination of the foot. So once we got the pitch, we wanted to make sure that we have good readings, and we started by putting phones on the shoes because that was the quickest way of getting access to inertial sensors. And then we simulated ramp environments inside the lab. We walked on these ramps, we stood at the same spot many, many times to make sure that the sensor gives us the same reading and that our readings are repeatable. And it turns out that the measurements that we were doing of the ground while walking, while standing, all through a standard inclinometer were very close, and the error was less than 0.5 degrees. So this is the trace we get from the complementary filter. This is continuous foot inclination. And now that we know how the foot moves at all times, we only need to know when it's in contact with the ground so that we can opportunistically sense the inclination of the ground. To do this, we divide this walking trace into phases of walking, and there are 4 phases: push-off, swing, heel strike, and stance. Stance phase is the one that we're interested in because that's when the foot is in contact with the ground. At this point, the inclination of the foot reflects the inclination of the ground. So we extract these stance phases, and for each of them, we find the slope, which is the tilt of the foot, the yaw, which is the horizontal tilt of the foot or the sideways turning, and the force, which is the magnitude of acceleration, and we consider that the force with which the step landed. We do this for every step that the person takes. And now when you walk, at every step, we have a measurement of the ground's profile. And we can see that when somebody walks down, there's a sharp decline. By looking at this small window of measurements, we can say that somebody is walking down a ramp and entered the street. But not all changes in slope indicate a ramp entrance. For this, we decided to look for patterns. The fall pattern is observed when somebody walks down a ramp. It's the sudden decline in the slope. We observe a rise pattern when somebody enters the street. Now this is because streets are curved outwards to let water run off. And in some cases, this inclination of the street is very noticeable. But we consider these low confidence events. And we consider a trough, a high confidence event, when we observe both of these patterns, which is the downhill of the ramp and the little uphill in the street. We use confidence for filtering and assigning some sort of confidence to the detection so that we can rule out false positives easily. Now, street entrances can also happen through a curve when people step off mid-block locations. And to do this, we use the force feature of our step, which tells us how somebody steps. The way we do this is by looking at the force with every step. We use dynamic thresholding, where we're comparing every step to a small window of steps in the last few seconds, and when we see a sudden rise, that usually indicates stepping off a curb. Now this warning comes at least one step when the person is in the street, but we hope that it's not too late, because a lot of times there are parked cars on the street and the warning is still useful for the pedestrian. We define a guard zone as an interval right after a high confidence event. So once we're absolutely sure that somebody entered the street, we set a guard zone. We discard all the values, all the detections that we get in the guard zone, which helps us get rid of false positives. But if I cross a street and if I turn and cross another street, we want to be able to reset the guard zone, for which we use turn detection. We use the gyroscope measurements to detect when somebody turns, and the guard zone is reset when somebody turns to look for another likely crossing. Also, the guard zone is set by using GPS and magnetometer readings, because we can get a sense of how far the next street is, so we have an estimate of how long it will take the person to make the next crossing. As a system intended for the real world, we tested ours in New York City, and the paths that we traveled are on the left, and in Turin, Italy, and the paths are on the right. So overall, in both these cities, 22 participants walked, crossing the street 1,670 times, a total distance of 112.5 miles, amounting to 80 hours of walking. And to give you a little perspective, all of this was in February. We installed GoPro cameras on all our volunteers just to see what they're walking and get a sense of what's creating false positives. I'll show some of the snippets from New York City. This is a typical ramp, and then we have a curb. This video here is most interesting because it actually shows the kind of environment we walked in. We're continuously walking around people and avoiding poles and trash cans and carts and slowing down and suddenly starting to walk. And we want to make sure that our system works in these kinds of settings also. Then this is an example of a false positive. When the pedestrian steps on this yellow curb, the system tends to think that you stepped off the curb, and it may create a false positive. For safety applications, it is important to understand the timeliness of detections. So we graph the delay distribution of the detections. The 0 on the x-axis is the point where the person enters the street. And we can see that most detections happen on the step right before the entrance, followed by the first step into the street. And the highest density of detections is in this small window right before somebody enters the street. So we use this small window as an evaluation window. Every warning that occurs in this window is still in good enough time to warn the pedestrian. Anything that occurs outside this window is either too early or too late to warn the pedestrian. And then we say everything inside is false positive and see how the system performs. We can see that in the intricate, complex Manhattan environment also, we can get 95% true positives with less than 1.5% false positives. And with the same false positive rate, we can get 90% of true detections in Turin. So the takeaways from this project...
So one question.
Yes.
What's qualitative? I mean, it looks like the lines are qualitatively different. What caused that? 5%?
Yes, and the reason I didn't tell was because I wanted you to ask. In Italy, they have cobblestone ramps. And we decided not to modify our algorithm at all. We didn't want to fine-tune it. So the exact same algorithm on the data that we got from Italy works a little worse because the cobblestone ramps tend to confuse the algorithm. So the takeaways from this project are that we can actually use shoe sensors for profiling the ground. We can identify exactly when somebody enters the street. And it also turns out that we can use these slope profiles to do sidewalk level localization. So imagine if a lot of people walked, which they do walk in New York City, we would have a unique sidewalk profile, a unique ground profile for every sidewalk. And we can use that to augment GPS and get a more accurate location. With this, I'll go on to the next topic of crossing detection using smartphone cameras. When people text and walk, their smartphone camera is actually pointed down and ahead to the ground in front of them. So we realized that if we could just capture these images and identify when they're entering the street, we could also use this sensor to want people to look up. Although material alone is good enough cue for human eyes to tell what's a street, what's a sidewalk, it's quite a challenge to get smartphone cameras to do this. We realized that in addition to getting a clear view of the ground ahead, the camera also sees a lot of other things like broken sidewalks and crowds and defaced streets, cluttered streets and whatnot. So we built a system which periodically extracts images from the pedestrian's smartphone, and we get a region of interest around the center because we realize that the center is usually the material of the ground ahead, and it's easy to get rid of the clutter which is along the edges. We use different kinds of features. We use intensity-based features, alternative representations like Fourier transform, which is the second figure here, and some texture descriptors to actually quantify the images that we get. We extract these features and use supervised training to train a one versus all classifier. And we're trying to do crossing detection. So what we do is we take all the images taken during a transition and all the other images of different materials, and then we try to say when a person is crossing the street. And for this particular project, we asked volunteers to walk around in different cities of the world and get us some data to see how different they are. And we observed that streets and sidewalks are made of different materials at different places. And we also wanted to see how well a trained model generalizes over these cities and how well can we do crossing detection in different cities of the world. So we realized that we can actually detect pretty accurately how people make transitions in Paris and London, not so well in Pittsburgh, and that's because in Pittsburgh, if they have brick sidewalks, a lot of time they'll have brick crosswalks also. So when you go from sidewalks to the crosswalk, nothing changes. And it's very hard for the camera to be able to say that you entered a street. But in Paris, interestingly, we saw that both streets and sidewalks are increasingly made of asphalt. So there's a very small concrete layer in between, which is a lot easier for the algorithm to identify compared to if it was the same material as brick in Pittsburgh. We tried to compare this camera-based approach to a gradient profiling approach and see how they compare. And we realized that while the gradient profiling approach is more accurate in detecting, the camera approach has less false positives. And the lack of common false positives is a good thing because it means that these systems are complementary. We can actually use them together. For example, if somebody is walking out late in the night, the camera may not be able to see the ground if the street is not well lit. But the shoe sensor can still pick up sidewalk to street transitions. On the other hand, a lot of times sidewalks and streets are not at different levels, they're pretty much at the same level, where the shoe sensor fails to recognize when somebody enters the street. But a camera can still pick that up. The crossing detection and the ground profiling that we proposed has many applications. The first is once we realize that somebody is entering the street, in addition to warning the pedestrian, we can also send this warning to oncoming vehicles. We can tell them when there's a pedestrian ahead, especially if he's not directly in the car's line of sight. We can use this as a feedback on crossing habits. So you could come back at the end of the day, see how your kids had been walking around, did they cross at designated crossings, did they run across the street, did they stop before they entered the street. We can also use this as an assistance for the visually impaired. And again, we can use this for crowdsourcing sidewalk health monitoring. Right now, the city has to send people out and they look for cracks and broken sidewalks, or the residents complain. But if we had this, then we could occasionally gather this data and build a database of where broken sidewalks were or where repairs were needed. This brings me to my last topic of infrastructure cameras. Cameras are everywhere. The United Kingdom has 5 million cameras, many of them in London, which has 1 camera for every 11 people. And other cities are rapidly catching up on the trend and widening their surveillance networks. The current state of surveillance, however, is automated, but only for traffic enforcement. a lot of it is still watched by a traffic operator staring at a wall full of displays, and he's trying to predict where congestion will occur and also detect unusual events. However, he shouldn't have to do that, because there are algorithms already that do that. Major advancements in computer vision have proposed algorithms that can model and find out how traffic behaves, how congestion will occur, and also detect unusual events. But there's a big disconnect. It's very hard. All these vision applications are meant to be used for when the camera is dedicated to that view. So I'll show examples later. But it's very hard to run multiple applications on the same camera. And what we're trying to do is break this one-to-one binding between camera and applications. Right now, cameras assume that they'll get viewed dedicatedly for one application. But we want to give that view to many applications so we don't have to install a new camera for every application. We want to support multiple applications at the same time. And we want to do this using existing cameras and existing vision algorithms. We don't want to reinvent anything, but we do want to fill the systems gap where it can share where different applications can share the view from the same camera. We realize that most of these cameras are steerable, which means that they have the capability to look around them. And we propose to use these cameras to support multiple applications. The camera can look at a wide range of scene and it can support different applications, whatever region the application are interested in. Often cameras are installed for a fixed application with a specific view in mind, and it's carefully adjusted. Its position, zoom, orientation is all catered to that one application. But we build a platform that allows adding many diverse applications to a single camera. And because the cameras are steerable, we want to be able to share that view with multiple applications. There are many challenges in sharing the same camera feed with different applications. First of all, applications are view specific and they don't adapt very well to changes in the camera. So if an application wants to look at a small region of the scene, it wouldn't work well if you keep turning the camera around. Different applications have conflicting views. An application that's tracking pedestrians might want to look at the sidewalks. Another application that's just doing volume monitoring might want to look at the lanes and the road, and if you want to support both the applications, the current way is to install different cameras and have them point at different regions in the scene. These cameras are mechanically steerable, which means that there's a certain latency in going from point A to point B. There's a motor that rotates them. And also steering commands from a remote location will reach the camera after a variable but potentially significant network delay. So the system has to be able to come up with a way to make up with that. Existing approaches either propose applications that directly steer the camera. So they directly issue steering commands, which also causes conflicts, or where multiple cameras coordinate to support one application. We propose Panoptis, and I'll start with a few applications. This is an example of a camera that's mounted specifically to look for cars that turn right on the red light. We see a lot of these cameras on toll booths, where the cameras are pointed to the place where your license plate will definitely show up and capture it in time. And this camera here is just monitoring traffic. It's counting cars, it's keeping a track of how many cars go towards the highway. There are two key insights. First is, most analytics applications are interested in a smaller view than the camera view. And the second is that most of these applications are looking for some form of motion in their region of interest. So based on these insights, we come up with two design principles. The first is virtual view abstraction. The goal of virtual view abstraction is to make steering transparent to applications. It aims to present an unchanged virtual view to applications, even when the camera has moved. And the second is mobility awareness. If the system can accurately predict when a moving entity will enter a virtual view, it can steer the camera just in time to capture that entity. So let's look at virtual views first. Virtual views are application-specific abstractions of the scene. Every running application has a corresponding virtual view, which is its region of interest. So the application at initialization can define what region it's interested in. It can ask for a specific resolution because different applications. So for example, a car recognition algorithm might not need high resolution, but if you're trying to read license plates, that needs higher resolution. It can also specify a frame rate. So if the license plate recognition application can only process 5 frames per second, then the system can actually give it 5 uniformly spaced frames. And when the camera rotates, for example, in this example, when we're counting cars that enter the WinLab parking lot, and the application is only interested in the small region. So even when the camera turns, the system makes sure that the application sees that small unchanged view. Now, camera views are basically small areas, small regions of the scene that the camera can see. And every camera view can have a different set of virtual views because the camera cannot see them all at the same time. So in one view it covers 2 applications, in another it covers a different set of applications. And it's defined by the position of the camera at that point, which is the pan, tilt, and zoom values, and also a small subset of the virtual view. But where should the camera look? How does the camera know where it should look at what time? Which brings me to mobility awareness. We base our system on the premise that cameras can observe and learn motion patterns from the scene, and they can use this information to predict if motion will occur in a virtual view. So the system observes the motion of all these traffic participants and tracks their trajectories. It then creates a mobility map, which is a 2-dimensional motion distribution over the scene. It identifies prediction zones. Prediction zones are approach areas leading up to virtual views, and they help in predicting motion. For example, these yellow boxes here predict cars going here, because a car that ends up here is very likely to show up in any of these prediction zones right before it shows up in the virtual view. So if the camera has the prediction zone in its view, that helps it predict motion in virtual views. So we anticipate motion to steer the camera just in time, for which it uses prediction. It has a lot of trajectories, and it uses that information to predict where each of these entities is going to be in some time delta t. And time delta t depends on the steering latency. And that's how the system keeps up with the steering latency. So if I know that the camera is going to take at least 1 second to turn over from any point to any other point, then it tries to predict the position of every entity 1 second ahead. Is this going to be in a virtual view in 1 second? Is this another one going to be in a virtual view in 1 second? And that's how it compensates for camera and network latency. So we have 2 key components, view virtualization and mobility awareness. The virtual view mapper takes raw frames from the camera. It extracts every application's regions of interest and provides it to the application. Then the predictor continuously predicts the future position for all the entities in the scene and provides it to the mobility-aware scheduler, which then controls the camera steering. And at initialization, the camera observes all the motion and creates a mobility map, which is used to generate prediction zones. So once I have all the trajectories, I can say where the prediction zone for any defined virtual view is, which is used to select camera view. And that's where it knows that it can see some prediction zones, some virtual views, and comes up with a list of candidate camera views. I'll briefly go over the implementation. We divide the entire scene into cells, and for each cell, we define a motion quotient, which is the probability of motion in that cell over the entire scene. Virtual views are composed as a combination of these cells, and every virtual view also then has a motion probability. And we want to use motion because we don't want to spend too much time looking at an application's view if not much motion happens there. So the objective of the mobility-aware scheduling algorithm is to maximize motion capture. And we define motion capture efficiency as the ratio of motion events captured over the number of motion events. I'll go over small examples. Let's say the blue boxes are virtual views. These are regions that an application is interested in. So the camera observes the scene, creates a mobility map, and identifies the prediction zones. Once it knows where the prediction zones and virtual views are, it tries to come up with a combination that fit in its camera view. So this is one combination it could look at, and this is other. Now it has to decide which one it starts at and how it goes from one to the other. So we define an importance metric, which takes the application priority into account, because some applications may have a higher priority. It also takes the probability of motion in the virtual view and in the prediction zones into account. So basically what importance metric is trying to say is, I'll try to serve higher motion, higher priority applications first, and then I'll move on to the others. So it picks this as the default camera view, which is where it starts, and let's call this A. If we had 4 candidate camera views, for example, instead of the 2, and it starts at A, the camera periodically steers to other camera views unless it's triggered by motion. So let's say it was looking at A, and then it steered to B, and then it steered to C, and suddenly saw this car that it knows is going to end up in view A because there's another application running in view A. The camera steers to view A, captures that motion, and then continues its periodic steer. I have a small video demo. So we're trying to count northbound cars and southbound cars. And these are the applications. So the system extracts this virtual view and provides it to the top application. And then it also extracts this virtual view and provides it to the bottom application. Let's say the system starts looking at this. So then the top application doesn't see anything. But the bottom application still gets the virtual view, and it can keep counting cars. When a car appears here, the camera makes a prediction that it's going to end up in the other virtual view, and it steers the camera to capture this motion. Now the bottom one didn't get any view. It makes a prediction again, and it steers again to the next one. In doing this, however, it does miss a car because there are simultaneous events, and the camera cannot capture both events at the same time. It can only look at a small portion. But we can see that by this steering, in a short clip, it can capture most of the cars, and it only missed one car. So we evaluated our system across diverse environments. We looked at a sparse traffic environment. We mounted a camera on the roof of the lab, and we simulated some pedestrian safety applications. We simulated some applications. Then we also mounted a camera on the 5th floor in core building on Bush campus. This looks at a huge parking lot where a lot of cars and students move. So it's a medium traffic environment. We got a lot of video from the New Jersey Department of Transportation from the camera that's mounted on Route 1. And we used these because, so the camera cannot look at all of them at the same time, but we simulate this motion so that we can quantify how much motion we ended up capturing. For the sparse traffic, we compared all of this to standard scheduling schemes. One is a fixed camera, which is the way things are done now, which will only serve one application. The other is round robin, which assigns a specific slot to every application. So it assigns a time t to one application, goes on to another, spends time t there. However, it's a little wasteful because if no motion happens in an application's virtual view at that time, then the camera is just sitting idly. Now, mobility aware actually performs better than the other two because it knows where motion will occur. And we can see that for a sparse traffic scenario, we can easily capture more than 90% of motion event from at least 2 of the 3 applications. And the colors here from dark to light represent application priority, which were just heuristically defined to see how the system works. And we can see that it tries to serve first the application with the higher priority and then goes on. For a medium traffic environment, round robin performs worse, but mobility-aware scheduling still captures more than 90% events for the highest priority application. It captures more than 80% for the second highest and then compromises some of the third highest. However, in a dense traffic environment, round robin doesn't work well at all. Mobility-aware still tries to capture a lot of the motion for the highest priority, but loses out on some for the lower priority applications, which tells us that when the density of motion in the scene increases, we need more than one camera. And we can always see how many applications can be supported on a single camera based on the motion density in the scene. So in conclusion for this project, we proposed view virtualization and mobility awareness for supporting multiple applications on a single steerable camera simultaneously. And we also discovered that as density of traffic increases, we need multiple cameras which can support a larger number of applications. I also worked on a few other projects while I was here, and especially the ones with car sensing and extracting automotive context. So smart city services include, but are not limited to, smart infrastructure where we want traffic lights to talk to us, traffic safety, especially for the vulnerable traffic entities like pedestrians and bicyclists, self-driving cars from the likes of Uber and Tesla, and the Internet of Traffic, where we want all of these entities to communicate with each other. I believe my research lies within this bigger vision of smart city for transportation services, and in the future there are some things that I want to focus more on. One is on the video analytics side. We want to train all these algorithms. We want vision algorithms to do a lot of the traffic analytics stuff that traffic operators are doing now. But they all need training data. So how do we scale this approach without actually having to gather training data for every application? Then again, collecting all of this data from people and reusing their sensors implies a lot of security vulnerabilities, which I also want to explore. I want to work on collaborative sensing between traffic entities, to have not each of them sense the entire scene by itself, but sense a part of it and exchange that information and learn more about the environment. I'm deeply vested in Vision Zero. My pedestrian safety work was the first step in injury prevention, and I want to do more of these. And Vision Zero is this international initiative for reducing traffic fatalities to zero. So in conclusion, I proposed sensing techniques for profiling the ground that a person walks on, which can help us, in addition to identifying exactly when a person enters the street, also identify when they enter the street at mid-block locations, and potentially be used for localization applications. We demonstrate that we can actually use mobile cameras and smartphones to capture the ground ahead of the pedestrian when shoe sensors may not be present, and be able to do some level of crossing detection using that. We automated camera control to steer a camera using motion patterns in the scene, and support simultaneously many data analytics applications. My years here resulted in few publications. Our pedestrian safety work was also fortunate to get the AT&T Connected Intersections Challenge Award and be featured in Wall Street Journal. Now, I know that professional service is not so PhD programs are not usually designed to encourage students to do professional service, but I did a lot of it, and I thank Marco for encouraging me to do that, and I wanted to put it here. Okay, so I would definitely like to thank Marco for all his years of hard work. I hope I can only be half the advisor you've been to me. I would like to thank all my committee members, Dr. Dana, Dr. Martin, Dr. Bal. My funding in the initial years came from Qualcomm. The pedestrian safety work was actually triggered by them. But then in the last years, National Science Foundation has funded us quite some to get going on these projects. I would like to thank everyone who walked in February. It was extremely cold that year. Everyone at WinLab, my master's advisors, especially Ivan and Rich Howard, for all their stories of mountains and physics and pretty much everything under the sun. And special mention to all those who made sure I was always caffeinated. You know who you are. At this point, I'm happy to take questions. Or not.
Can you go back to the slide on the results with dense, medium, and light? Yeah. What is LPR?
License plate recognition. So we simulated different applications based on what kind of scenario it was.
So you have that at 60% in the mobility aware case, right? That's 60%.
Right, because I gave it the least priority.
I see.
So the darker color means higher priority, and then the red is lower and yellow is the lowest priority. And the system always tries to support an application with higher priority and higher motion content.
So do you have a guess as to how this would change if suppose you could steer or switch between the views much faster?
So that would be a 360-degree camera, which we believe could be the future. So one of the things we wanted to do was target a system to existing cameras, which are steerable cameras. But I believe that the proposed techniques can also be used for 360-degree cameras, which are higher resolution. So the cameras still don't have to send the entire image to the cloud. They can extract these views simultaneously, conserve on bandwidth, and then send only what's important back for processing. So it would spend no time in steering latency, but the view virtualization would still be useful in sending high-resolution virtual views back.
I also have a question about this slide. Assuming that some applications have the same priority, for example, you want to know the northbound traffic and southbound traffic equally, would you think your approach will converge to round robin, or it will perform better?
So we tried. It still performs better because round robin doesn't care about whether or not motion happens in the scene. But mobility aware will still try to only spend time at a virtual view if it knows that motion is going to occur there. So it still captures more event, but if you give two applications similar priority, then their motion capture would also be nearly similar.
So I have lots of questions. Ready for committee questions? Or Let's go to the complementary filter. Can you give me some intuition of why you use that? What does the combination of high pass and low pass do for us?
So the high pass filter gets rid of the errors caused by the gyroscope drift, and it only keeps short-term changes because gyroscopes are very accurate in the short term, but they do accumulate error. The low pass filter gets rid of the lag that comes from the accelerometer. So by combining both of these, the overall filter has much less lag than if we were only using low pass filter with an accelerometer. So the combination sort of defines a weight as to how much of the gyroscope readings we want to use compared to how much of the acceleration we want to use. So the alpha parameter here will define that weight. So we might want to use more of the accelerometer and less of the gyroscope if the device is not moving, if the sensor is not moving, because then the gyroscope doesn't give us anything, but the accelerometer still gives us a pretty good estimate. So this combination helped us with the lag and the accuracy.
And how do you get the coefficients?
So the way we got this coefficient was, I think alpha is defined, we did it for, if your gyroscope drifts, say 2 degrees per second, and we don't want the time constant to be more than, say, a second, if that's the most we can afford. And using the time constant, we defined alpha. So I think we used a tau of 0.75, which gave us an alpha value of 0.96.
So sort of a combination of physics-based motivation and tweaking.
Yes, physics-based motivation and then some empirical tweaking based on what works best for your case, because different cases have different noise levels. So we tried a few values for ours and we realized that a value of 0.75 seconds worked well for us. It didn't give us a lot of errors.
What gives false positives?
For the shoe sensor?
Yeah. And is it dependent on the type of shoe?
It's not dependent on the type of shoe because all the volunteers who walked, we didn't give them shoes. We just strapped the sensor onto their shoes.
Did any of them wear high heels in February?
No.
That's good.
So false positives are caused a lot by if the sidewalk's broken, or if a lot of times in the middle of the sidewalk, a lot of times the level changes. These are the ones we observed from the videos. Then there was the one that I showed where there was a big patch people had to step on. So if you stepped on that and then you stepped off, the system would think that you just stepped off a curb and it probably missed a turn. So these were the ones that caused a lot of false positives for us. Disturbances in the sidewalk.
Okay, that's good. What are your thoughts about sensor networks among the shoes and how you might use them?
So we did actually think about it, that if pedestrians' shoes can talk to each other, especially in dense Manhattan-like environments, then we can actually use that to control pedestrian traffic lights. We know when a big group of pedestrians is walking towards a traffic light, we can communicate that information to oncoming cars, and maybe even get rid of traffic lights. We can do all of this over sensor networks because cars have sensors, people's smartphones and shoes have sensors. So the whole platooning system might work better where a large number of pedestrians want to cross a car and we can control the traffic lights. So that was one of the things we thought about.
I was also thinking maybe the person ahead, if you have identified two people as walking up in front and behind each other, then the person ahead crosses an intersection, then you have a prior for the person behind them to cross the intersection.
Right, yes, that too. So they can sense and communicate.
Did you at some point in the project try to use lane markings? And let me preface this. You can see from the pictures you showed, and also I thought it was very interesting, the automated driving tests recently were affected by the quality of line markings.
Right.
And I was very happy about this because I personally can't see the road in New Jersey anymore because if it's nighttime and it's raining, I tell everybody this, I can't see the road, there's no lane markings.
Right.
So I know that they're not going to paint it for me, but they might for automated driving systems. So what were your experience, what's your experience in trying to use lane markings to detect?
So we did not use lane markings for the smartphone camera work. We were mostly focusing on the kind of material. So because the strips that separate streets and sidewalks are usually of a different material than what the sidewalk is made of.
Yeah.
But it didn't have to do anything with painted markings. And the streets also, we didn't try to use the crosswalk markings. We really just tried to detect the ramps and curbs, but through the smartphone camera.
Okay. This is a specific question on slide 30. Can we go to slide 30?
Yeah, I think my laptop froze.
Oh, okay. So slide 30.
It'll come back.
If it froze, I might be able to just describe it to you.
Well, the Skype timer is running, so I don't know if Victor is here.
I'm here, but there's a lot. I'm here, but there's a lot of noise, background noise. Can you hear me?
Yes.
We can hear you.
That's your fan.
And is it clear?
Okay,
There we
now
go.
it works.
Yes, it's very clear.
Oh, okay.
So there was, on slide 30, okay. So you have all these detections. Before you're entering the street, you have all these positive detections. And I didn't understand what was happening here. Why would you know that you were entering the street?
These?
Why would you know you're approaching the street? Is this still the slope?
Yes.
Oh, okay.
So this graph is a combination of ramps and curbs, which is why we see a lot of them at the first step in the street. But the ramp lengths differ a lot. So if the ramps are longer, plus people's stride lengths are different. So we realized that the 7-step window before somebody enters the street seemed to work for most people. So you could either get less than that or about 7 steps, and that's when we start seeing detections because that's when the slope changes. And this is the small window over here.
And you feel that you need, you also talked about including the uphill part, and that gave you a much better signal. The
Right.
problem is the person's already in the street though.
Yes, but usually that uphill is very sharp. So after that sharp decline, we only keep up to 1 step for that uphill. And even the patterns had that in 1 step because that doesn't change as slowly as ramps do. And it's more subtle than ramps.
Okay, the next 2 questions are about looking past the methods that you used to some other things. They're sort of standard, they're sort of what people in computer vision would ask you, I think. One is, have you thought about using catadioptrics, omnidirectional cameras in this work? Those are, are you familiar with them?
A little.
They're the convex parabolic mirrors.
Right, yes.
What are your thoughts there?
So I think they can be used, and I can think more of them for localization. So if you can see, look at the scene. This is for the smartphone camera work.
The steer, right, it would replace the steerable
the
because you're
surveillance
seeing
camera.
all views.
Yes, so that's the one where we won't have any steering latency because the camera can actually look all around.
Right.
But we hope these cameras will have higher resolution. So if it has a parabolic mirror image, if it has a single construction, then if it's higher resolution, it can still extract images and save on bandwidth. And a lot of the 360-degree cameras now have multiple cameras attached to a rig.
Yeah.
In that case, it can still control the precise camera to say zoom in for license plate recognition. But the 360-degree cameras one I think is very useful for saving on bandwidth.
You did mention, you did nail on the exact problem, which is resolution. You get the whole 360 degrees for free, but there is some issues in resolution if you're only using a single camera. And the last question is deep learning. How would you use deep learning in this project?
So I think we can use deep learning, at least for the smartphone camera pedestrian safety, to do better detections. It's just that we wanted to use simpler techniques, one, to see if it actually works. Second, deep learning still requires more compute resources than we have tested with smartphone cameras. And I'm pretty sure that very soon we can use a lot of these complex models on smartphone cameras. So that's definitely worth trying, and I think it might make the system better. And
Most of the computation is on the training side.
on the training side, so we can train a model and then put that. So yes, that's definitely the next step. The work that I did was more exploring, can we actually even do that? Can we capture good enough images in all kinds of environments to test it with basic texture recognition techniques? So the next step would certainly be using more sophisticated algorithms like deep networks and trying it out.
Do you have enough training data for that yet?
Well, we have a lot of images from different cities, and other than the 4 cities, we actually collected a lot of other data that I didn't get time to process and label because we were doing all the labeling by myself. So, yes, I think I have
all of your data are video, right? So for
They're all
every
videos.
intersection, you have all of those frames leading up to the intersection.
Yes.
So each intersection, you have many images, right? Which
Right.
will look a little bit in the data.
Any other questions from the audience? And I think we'll excuse the audience and continue with other committee questions. Unless you want to ask about it.
You can take any message from them you like.
So I should.
Yes, yes.
Okay. So we should talk sometime about what you